Welcome back, everyone. In this video we're going to cover problem number 5 in the chaotic review. So problem number 5 asks us for which value of x is the curve y equals g of x closest to the point 16 comma negative 1/2. And so we really need to search our mind for a while to figure out, right, how can we use calculus to solve this problem? And so after hopefully a little bit we identify there's a key word here, closest. Closest means smallest distance or shortest distance. And so actually this is an optimization problem, right? We want to minimize distance. And minimizing distance, right, that was something that we can do with optimization style questions. Okay, so if I want to minimize distance, I better have a distance formula. So let's go ahead and break out our distance formula, right? Originally your distance formula is given by the square root of x2 minus x1 squared plus y2 minus y1 squared. And again, this is all under our square root here. This is meant to be the distance between the point x1, y1 and x2, y2. So that's our distance formula between these 2 points. Now, reading our problem, one of our points is fixed, right? We have one point is 16 negative 1/2. That's a fixed point. But our other point, we don't know really so much about it except for that it's on this curve, right? So that one's not fixed. It's somewhere on the curve, but it's not necessarily pinned down at a particular point. So let's go ahead and start substituting some of this stuff in here. So for instance, maybe I'm going to have this be my x1, y1. And then for our curve, again, we can't really fix this. It's just going to be a point x comma y. So that's going to be my x2, y2, my second point. But again, it's not fixed. All right, so let's go ahead and maybe plug some of this stuff in. So x2 in this case is just x minus x1, that's 16, quantity squared, plus y2, that's y, minus y1, that's negative 1/2. So minus a negative, that'll be plus 1/2. Now we do actually have some information about how x and y are related on this curve, right? Because it's y equals g of x. So in this case we have y is equal to, and g of x is the function x squared minus 1. So actually, right, I'm looking at this and I'm thinking, okay, optimization. That means I'm going to need to take a derivative and I'm looking for critical points and all that sort of stuff. But I don't like that there's 2 variables still, x's and y's. So actually the fact that this point is on the curve, y equals g of x, x squared minus 1, this will enable me to get rid of my y's and get down in terms of just one variable. So I'm going to go ahead and rewrite this one last time here. X minus 16 quantity squared. Plus, and again, instead of a y here, I'm going to write x squared minus 1 plus 1/2. Actually, even let's simplify this down, right? Minus 1 and plus 1/2, that's going to be the same thing as minus 1/2. Quantity squared, again, we're all under our square root. And now we have a distance function, but it only has one variable. So this is the thing that I want to minimize. I want to find the smallest distance, right? The closest. Right, smallest distance for this distance function. All right, so again, if I'm interested in minimizing, then really I want to take the derivative and I want to search for critical points, because critical points have minimums, they have maximums. There are also boring critical points, right, that are neither minimums nor maximums, but right, there are minimums amongst critical points. So I'm going to start searching for critical points. So now let's go ahead and take the derivative. Which that's good because, I mean, we're in calculus class after all, so hopefully there was a derivative or antiderivative or something, you know, calculus related eventually. So let's go ahead and take the derivative of this. Remember, the square root here on the outside, this is being raised to the 1/2 power, right? Square roots are the same thing as 1/2 power, so I'm going to go ahead, bring that 1/2 down, leave the inside alone. And I'm going to reduce that power by 1. So it goes from positive 1/2 to negative 1/2. Then we multiply by the derivative of the inside. So the derivative of the inside, well, let's see, the derivative of x minus 16 squared is going to be 2 times x minus 16 plus the derivative of, let's see, x squared minus 1/2 squared. This is a little bit more complicated, but again, I bring down the 2, leave the inside alone, and then I multiply by the derivative of the inside. So the derivative of x squared is going to be 2x. All right, that was the derivative of the inside. Again, that's the derivative of x minus 16 quantity squared plus x squared minus 1/2 quantity squared. This looks a bit messy though, so let's go ahead and maybe simplify down. First of all, I notice there's a 1/2 here, and maybe that'll cancel out with the 2's in both the terms here. So that's a little bit nice. Another thing is that we have this raised to the negative 1/2 power, so I'm going to go ahead and push that into the denominator, and remember that 1/2 power is the same thing as the square root. So we're going to have x minus 16 quantity squared plus x squared minus 1/2 quantity squared. Again, this is all under our square root here. Okay, what's left in the numerator? Let's go ahead and simplify this down a little bit. Let's see, I'd have an x minus 16, and then plus, and let's see, I have 2x, and I have to distribute this maybe to each term. So I'm going to distribute that to each term. So 2x times x squared is going to be 2x cubed, and then 2x minus 1/2, so that's going to be negative x. And actually there's a little bit more cancellation then, right? Because we have a positive x and we have a negative x. So those are going to perfectly cancel out. Okay, so again, let's think about what we're doing here, right? We're trying to find critical points. Critical points occur whenever the derivative is undefined or whenever the derivative is 0. So let's first try to figure out if the derivative can ever be undefined. And so when I'm looking at this, well, derivatives are undefined maybe when you're dividing by 0 or when you take a negative and you input it into a square root. So these are some things that I'm mildly concerned about, right? So first of all, I have a square root. However, I notice that I'm putting in something squared plus something squared, right? So this is going to be positive, or at worst case 0, plus positive, or at worst case 0. Right? So if you're plugging in two positives and adding them together, right, this is just going to be more positive, right? So therefore, there's not any negatives that you can actually input into this square root. So we don't have to worry about that. The other thing, right, what if this was equal to 0, right? Because if it was equal to 0, then I'd be dividing by 0. Now, luckily, that can't occur either. And we can see that, again, you can kind of convince yourselves that you have positive plus positive, and the only way in order to actually plug in 0 into this thing is if both of these terms, maybe I'll underline them in green, if both of these terms were equal to 0 at the same time, right? Because then you'd have 0 plus 0, and that's what would make it 0. But if even one of them is not 0, there's no way this can be done. So what does it take maybe for the first term to be equal to 0? Well, you'd have to have x's equal to 16. That's the only way that you could make this equal to 0. Okay, but does that work in the second term? Absolutely not, right? You'd have 16 squared minus 1/2, right? There's no way that's equal to 0. So in fact, there's no place in which this derivative of the distance is undefined. So our only hope for critical points are when this is equal to 0. So when this is equal to 0, let me go ahead and rewrite the top here. 2x cubed minus 16 divided by the square root, and I'm just going to freehand this a little bit. I don't recommend you do this for the exams, but it's the square root of stuff. The reason why I write it like this is because, well, the very first step in trying to figure out when it's equal to 0 is I'm going to say, well, I hate fractions, right? So I'm going to go ahead and multiply through by the denominator on both sides, and luckily 0 times anything, right, the square root of all that stuff in this case, but 0 times anything is just going to be 0. And so this is going to nicely simplify down to 0 is equal to 2x cubed minus 16. Now I can go ahead and add 16 to both sides. So I get 2x cubed is equal to 16. I can divide by 2. And finally I can take the cube root. And when I take the cube root of 8, right, what cubed is equal to 8? We get the answer 2. And so 2 is a critical point. However, if this was to show up on an exam, right, and I just say x equals 2, done, right, I'm going to expect to lose some points, right, because it is a critical point, but I haven't shown that it actually minimizes distance. What if it maximized distance? Or what if it was a boring critical point, right? So I have to show that this actually minimizes distance. And so the way that I'm going to do that is by drawing a number line here. And I'm going to split up that number line at all of our critical points, or all our critical numbers. So in this case, there's just the value 2. Remember, I'm going to be plotting information about the derivative. So let's go ahead and choose some test points here. For instance, maybe like 0 and like 3. You can choose your favorite points. And we're going to again plug these things into the derivative. All right, so I'm going to be looking maybe at this line up here. All right, so if I plug in the value 0 everywhere I see an x, well, let's see. In the numerator, I would have negative 16. And in the denominator, I'd have the square root of, let's see, 16 or negative 16 squared. But when you square it, right, it's going to become positive. Plus, and let's see, 0 minus 1/2. So that's going to be negative 1/2. But when I square it, again, it's going to become positive. This is maybe some bad notation here, but yeah, this is positive plus positive, right? So again, kind of the thing in the denominator is always going to be positive. That's basically just what I wanted to write down. So I have a negative on top divided by a positive on bottom. So therefore, at 0, the derivative will spit out some negative value. Again, I don't particularly care what negative value it is, only that it's negative. How about if I was to plug in something like 3? So if I plug in something like 3, what happens to the numerator? Well, let's see. I would have 3 cubed, that'd be 27, times 2, that would be 54. So I'd have 54 minus 16. And again, so this is going to be positive on the numerator. And then in the denominator, I'm going to have the square root. And if I was to plug in 3, let's see, I'd have 3 minus 16, that'd be negative 13. But when I square it, it'll be positive. Plus, let's see, 3 squared would be 9 minus 1/2. That's going to be positive, and when I square it, it's still going to be positive. So it's going to be positive plus positive. So when you take the square root of positive plus positive, it's going to certainly be positive. And so I'm going to have positive in the numerator, positive in the denominator. So at 3, it's going to be positive. And so, okay, we need to use, right, this kind of first derivative test thing to determine, right, what's happening at 2? Well, it was decreasing, right? It had a negative derivative, and then it's now increasing after 2, right? It has a positive derivative. So therefore, at 2, we have a minimum. So this is the necessary work that we need to show to prove, right, that at 2, we actually minimize distance. Because again, there are boring critical points. It could be a maximum, something like this. So this is the work that we need to say, so x equals 2 minimizes distance. And the last thing we need to do is go back and read our problem, right? So our problem, sometimes it can ask for what is the minimum distance, or maybe it asks for what is the point, right? An x value and a y value that minimizes distance. So we need to make sure that we've answered the question that was posed. So in this case, it asks for what value of x. So notice it doesn't ask for the y value. It doesn't ask for the point, right? If it asks for a point, we need the x value and the y value. It just asks for what is the x value of the curve that is closest to this point, right? So it doesn't ask for us what is the distance or anything like this. It just asks for what is the x value. And so this right here does answer the question. So we just have to go back and make sure, right, that we're answering the question that was posed for us. So again, x equals 2 is the final answer. This is the work that we would need to show in order to prove it. All right, that's it for this video. I'll see you guys next time.